Hello, this paper presents bifurcation analysis to identify voltage collapse in Bangladesh power system. The research was conducted by Mohammed Karam Moni Rabi, Dr. Abdul Hazib Chowdhury, Mohammed Ali Azam and Mohammed Asaduzaman Tawfiq from the Department of Electrical and Electronic Engineering at Bangladesh University of Engineering and Technology, Bangladesh. I will structure the talk as follows. First, I'll define the problem of voltage collapse. Next, I'll discuss our proposed mitigation strategy using SVCs. I will then explain the core analytical technique we used, bifurcation analysis via continuation power flow. After that, I'll describe our system model of the Bangladesh grid. Finally, I'll present the key results and our conclusions. Let's begin by understanding the core problem. Voltage collapse is a major threat to modern, heavily interconnected power systems operating near their stability limits. As per the IEEE definition, voltage collapse is the process where instability leads to a significant loss of voltage. It's typically triggered by a disturbance or load increase. The key point is that both operator actions and automatic controls fail to stop the progressive voltage decay, which can eventually lead to a widespread blackout. In our study, we treat this as a steady-state stability limit problem. This classic nose curve illustrates the fundamental issue. It plots the voltage at a load bus against the power delivered. As we try to draw more power, the voltage drops. There is a critical point, the saddle node bifurcation point, beyond which no steady-state power flow solution exists. Operating beyond this point leads to a rapid, uncontrolled voltage drop. This is the voltage collapse. Our goal is to identify this point for the Bangladesh system and push it further out. To mitigate collapse, we need to support the system voltage. Our chosen method is reactive power compensation. We propose using static VAR compensators, or SVCs. These are fast-acting devices that inject or absorb reactive power. In the Bangladesh system, capacitive shunt compensation already exists at 33 kV substations. For our aggregate 132 kV bus model, we propose strategically placing SVCs to perform two key functions: first, to reduce the effective inductive impedance of the transmission lines, and second, to directly regulate and support the transmission voltage, especially under heavy inductive load conditions. To understand the need for compensation, consider this simplified east-west transfer scenario. With all lines in service, transferring 3000 megawatts requires 300 MVAR of reactive power from the eastern generator, which is well within its 1200 MVAR limit. Voltage is stable at 1 per unit. If one line is out, the same power transfer requires more reactive support per remaining line, 362 MVAR. The generator is still within limits, but the system's stress has increased. With two lines out, the reactive power demand on the remaining lines jumps to 453 MVAR. Now, the eastern generator hits its 1200 MVAR limit. This is a critical, stressed operating point. Any further increase in load or disturbance could lead to instability, highlighting the need for additional, decentralized reactive support from SVCs. To precisely identify the collapse point, we used a robust mathematical framework, bifurcation analysis. A bifurcation represents a qualitative change in a system's behavior due to a small parameter change. For voltage collapse, we look for a saddle node bifurcation, SNB, which corresponds to the maximum loading point on the nose curve. We used specialized software called UPFlow to perform a continuation power flow analysis. This method gradually increases the system load parameter, lambda, and traces the solution curve, reliably finding the SNB point where the system Jacobian becomes singular and the voltage collapses. Now, let's look at the actual system we modeled. Our model is based on the actual Bangladesh grid. Bulk power is generated in the eastern grid and transferred west via two key 230 kV tie lines, Gorus Lishurdi, first EWI, and Ashiganj Sirajanj, second EWI. We created an equivalent east-west interconnected system, or EWIS, for our analysis. This map shows the topology of our reduced EWIS model. You can see the major load centers and the critical east-west interconnection paths we just mentioned. Our analysis focuses on identifying the weak buses in this network. Here are the key findings from our bifurcation and load flow studies. Our analysis found that the uncompensated system experiences voltage collapse at a loading factor, lambda, of 0.98. This table identifies the specific buses most affected by the collapse, such as Barisal and Faridpur. The corresponding affected near buses column shows that voltage collapse is a localized but spreading phenomenon. When a key bus fails, it drags down its neighbors. Buses marked with an asterisk are less affected, often because they have better support from nearby generation. This diagram visually summarizes the previous table, highlighting the most vulnerable buses in the western region of the Bangladesh grid that we identified through our SNB analysis. To mitigate the collapse at these weak buses, we performed a load flow analysis to determine the exact amount of reactive power, MVAR, needed at each location. As shown in this table, the total compensation required is about 75 MVAR, distributed across 6 critical buses. For example, Chapanurbagan needs the most support at 19.4 MVAR. The results are very positive. By placing SVCs with the total 74.77 MVAR capacity at the identified buses, we increased the system's maximum loading factor from 0.98 to 1.04. This is a 6% improvement in loadability. Furthermore, the voltage profile across all buses improved significantly. This chart for Purbasidepur is an example, showing how the voltage versus loading curve shifts upward and rightward with compensation, indicating a more stable and robust system. In conclusion, to summarize, we have successfully determined the voltage collapse constrained loading limit of the Bangladesh power system. Using bifurcation analysis, we identified the weakest buses in the western region. We then demonstrated that targeted SVC placement, providing about 75 MVAR of reactive support, can increase the system loadability by over 6% and improve voltage profiles. For future work, this preliminary study should be extended to include contingency analysis for generator outages and, importantly, more realistic mixed load models to improve accuracy. The research bifurcation analysis to identify voltage collapse in Bangladesh power system is an ongoing process, and we welcome any suggestions or insights. If you have any questions regarding this work or are interested in collaborating on future research in this area, please feel free to contact the authors via the provided email addresses. Thank you for your attention and interest.